So now we're in a world where we're actually doing hypothesis testing. Last class we went over difference of means tests. So you have two groups, the variable of interest that you've measured, whether it's time, the amount of seconds it takes to get out of a parking spot, or the amount of jumps you can complete in 30 seconds, or the number of words you can read per minute. We went over two situations in class, one where you have two samples that are of the same size, and another one where we have two samples that are of different sizes. And then the video that I did handled difference of means when you have the same sample twice. So you have a pre-test, post-test situation. We started rejecting null hypotheses. So we started to say, based upon the sample that we have observed and collected, that sample is so different from our theorized population that there must be a relationship and we can reject the null hypothesis. What we're doing is relying again on probability, on the likelihood that we observed our sample, whether it's a difference of the means, that came from a population that had no difference. So there's no gender difference in the population. How likely is it that we observe a difference in our sample? And if it's very, very unlikely, if the probability of our sample difference is very low, then we can reject the null hypothesis. We have to remember that what we're dealing here with is probability. So we made that sort of leap in chapter 5 when we went from just talking about the area under the curve as the percentages of a grade distribution. And if you were in this part of the curve, you were in the top 10% of all the people, right? We treated that area under the curve as a percentage. But now we're treating that area under the curve as the probability of observing that spot in the curve. So because of this, our hypothesis testing, we can actually get the wrong result. And we've talked a little bit about this before. The idea of false positives and false negatives. So imagine there was a case where we were talking about polygraphs. Polygraphs are psychophysiological responses to questions. So the simplest version of a polygraph is a heart rate monitor. We'll see if your heart rate increases when you lie. If we interrogate 68 people using a polygraph and we know whether or not they were trying to lie or not, we can see how accurate the polygraph was. So when it comes to making a decision, we very frequently use this 4 squared box idea. Right? So on the one hand, we have what the polygraph told us. So this is our test. Or our sample. And we compare that to the population. Or truth over here. Now, if the polygraph says you're guilty, that you're a liar, and you probably did commit that crime, but in reality you were innocent, you just had a bad test, that's an incorrect decision. That's an error. But if the polygraph says you're guilty, and you are guilty, well then the polygraph worked. If you're not truly guilty, and the polygraph says you were innocent, that you did not commit the crime, that is also a correct decision. But if the polygraph says you're not guilty, but in reality you were, so you defeated the polygraph, that's another form of error. So we have two ways in which you could get it right, and two ways in which you could get it wrong. So let's put some numbers to this. The polygraph said 17 people were guilty. Right? The polygraph said these 17 people were guilty. But of that, only 16 were actually guilty. Sucks to be this guy, right? You were actually innocent, but the polygraph said you were guilty. 51 people, the polygraph said were not guilty. But 14 people tricked it and were actually guilty. So that's 14 people that got away with crimes. So these 15 people were wrong. They're errors. These are two different types of errors. I've mentioned this in class before. We have what we call type 1 error and type 2 error. Type 1 error is when we have incorrectly said a relationship where we should not have gotten one. This, I think we can agree that this is the most dangerous one and the one that we want to avoid the most. Can we all agree that we would rather let 14 criminals go than put one innocent person in jail? And why do we all agree to that? Huh? Not necessarily. Okay, because it would suck if you were the one person that went to jail. And we all want to not be that one person that goes to jail, right? Because generally speaking, we all think we're innocent people. Or at least if we aren't, then we know we're not. But generally speaking, let's just say we're all nice, innocent people, and we would not like a situation where we could go to jail, even though that we are innocent, because some box said we lied. Why is it okay to let 14 criminals go free? Yeah, we'll get them eventually, right? Criminals are stupid. My dad was a retired police officer, and he told me that I don't know how many times. It's like, don't worry about it. Criminals are stupid. It's like, all right, Dad, pretty clear and forceful on that one. So this is the one that bothers us the most, this type 1 error. For us, a type 1 error is when the null hypothesis is true. So that would say that there's no relationship. But we accidentally reject the null hypothesis. And we say that an effect exists. So back to my spanking example, we would incorrectly say that there is a gender difference between men and women when it comes to spanking children, when in fact there is no difference. It just so happened that my sample was different than the population. The probability that we make this error is our decision rule. It is alpha. So whenever we're doing a problem and it says state your decision rule, what's your alpha, we're deciding what probability we want that we're making a type 1 error. So if we set alpha to 0.05, then we're actually saying that there's a 5% chance of concluding that an effect exists when it doesn't. A 5% chance of incorrectly rejecting the null hypothesis. So what's the solution to this? How can we fix this problem? How can we fix the problem of type 1 error? Make it really high? Okay, we have control over alpha. It's our decision rule. So if we wanted to, we could make alpha really, really small. And by making alpha really small, that makes the probability of making a type 1 error really, really small. What does it also make the probability of really, really small? Because we could do that, right? We could set alpha to 0.00000001. And we would never incorrectly reject the null hypothesis. But how would we have achieved that? How? How would we achieve never correctly rejecting the null hypothesis? Yeah, by never rejecting the null hypothesis, right? We will never find a relationship between two outcomes. We'll never find that relationship. But because we'll never find a relationship, we'll never falsely find a relationship. This is the idea of, I don't want to break up with somebody, so I'll date nobody ever. Which when I say it like that, you're like, that's stupid. Right? If I never want to get divorced, then I should never get married. Problem solved. And if I never want to get divorced, I should never date anybody ever. Okay, but that'll make the probability of you actually having a successful relationship 0. When you think about this just in terms of avoiding that 1, right? This 1 here, what are we throwing out? To avoid that 1 as much as humanly possible, what are we throwing out? What are we sort of reducing actually happening? What we are, when we change alpha and we make it really, really low. Right? Remember, we don't want to be this one person. What are we losing when we make alpha so low that we never reject the null hypothesis? Right? What's it going to take to turn that to 0? What? Yeah. We're going to lose these 16, right? So there's a benefit. If we set alpha too low, we have to think about it in terms of, well, what are we more likely not to do? So if we have a 5% chance of making a type 1 error, that means that we have a 95% chance of not making a type 1 error. So we can increase this as much as we want, but that's still pretty good. Like, it sucks if you're the one person in jail, but still 95% is still a good shot. There's not much in life where I can tell you that you will have a 95% chance of succeeding and you'll be like, no, sorry, there's still that 5. Not going to do it. All right, let's go to Vegas and I'll show you the magical game where you win 95% of the time. And you'll be like, sorry, that's not good enough odds for me. But yet you go to Vegas and you willingly play games where you have less than a 50-50 shot at winning. Your chances of winning the lottery are in the billions. Like 1 in many billions. But yet you're like, I'll play. Not a problem. So when you think about it, even though it's 5%, again, it's not 95%. We have a not 95% chance. That's pretty good. Why are we concerned about this? Well, listen, my stupid example about whether or not we spank my kid or not, it's fake, it has no real meaning. But when you're using these statistics to make decisions, we have to be careful that we're not conveying false information. I think this is the most important for things like the biomedical fields that use these methods, these exact methods all the time when they do drug trials. What would be a negative if we conveyed false information? Imagine a drug trial in which there was no improvement in depression or some other illness, but the researchers claimed that there was. What's the consequence? So what's the consequence of taking a pill that has no influence on your treatment, on your disease, on your malady? How do you mean make it worse, Gregory? Yeah, you might be pissed off. You're like, oh, geez, this works for everybody else, but not me. I'm a horrible person. Could make your depression worse. What else? There could be side effects. So the ridiculous yawning that comes with things like Prozac. My dad took some cancer drug. It turned his teeth gray. That kind of sucked. What else? What else is there a reason why we don't want to have false information out there? If you're undergoing a set of treatments that don't work, so you take pill X for your malady, what aren't you doing? Actually fixing your problem by doing what? Yeah, some other treatment. Okay? So with cancer, lots of times you have a choice between radiation, chemotherapy, or surgery. Well, if the chemotherapy doesn't work, and you do chemo, and you can't do the other two at the same time, you're not doing anything. So one of the consequences is that we're sort of wasting time. Economics likes to call it an opportunity cost. Right? The opportunity cost of doing something that won't lead to the result when you could be doing something else that could lead to the result. So why does this happen? Well, the main problem is sampling. Have I told you guys how to eat soup before? I haven't told you that yet? Oh, can't believe you almost got out of a class with me about learning how to eat soup. Who would like to have a ridiculous, detailed conversation with me about how to eat soup? Any volunteers? You're all scared. All right, Lorenz. Do you like soup?
Yes.
What kind of soup's your favorite soup? Chicken noodle soup? I can't talk to you. What's in chicken soup? No noodles? This would work a lot better if you like noodles. Okay. Do you remember when you were a kid and you had like the Campbell's chicken noodle soup? What was the best part about the chicken noodle soup? No, not about like the ease of it. What was the best part of eating the chicken noodle soup? The noodles. Okay. Those little tiny noodles. You can actually buy those noodles. All right, so just next time you're in the store, look for those little tiny, like, really just broken up spaghetti, but little tiny noodles. All right, I have made you your favorite chicken soup. I've put it in a bowl. I put it down in front of you. It's not too hot, so you have to blow on it. Give you a spoon. What's the first thing you do to eat your soup?
Pick up the spoon.
Okay, you pick up the spoon. You then do what with the spoon? And then do what? You eat soup wrong. I'm not kidding. You eat soup wrong. No, you don't need to ask for a fork. You eat soup incorrectly. Who here eats their soup incorrectly like Lorenz does? See, you're so ashamed you won't even lock the elbow and raise your hand. And then, yeah, that's wrong. No, I told you, it's not that hot. Like put it to your mouth? No. What? Yeah, you're right. You're supposed to mix your soup. John, why do you need to mix your soup? Yeah, stuff settles to the bottom. That was the worst part about the chicken noodle soup. It was that there weren't a lot of noodles in it. It doesn't matter. No, it does. Noodles sink. Noodles sink. I make my own chicken noodle soup. And the problem with the way I make chicken noodle soup, according to my wife, is I put too many noodles in it, and it's no longer soup. It's a noodle dish. Exactly. See? Here's the problem with things like chicken noodle soup. The noodles in the chicken float to the bottom. Sorry, that's not float. They sink to the bottom. All right? And so if you just make your initial foray into your soup, you're just going to get nothing but broth. Agreed? So, agreed? Yeah. So here's the correct way to eat soup. You stir your soup. Why? Because when you're eating chicken noodle soup, the correct bite or spoonful of soup includes everything in it. The chicken and the noodles included. Right? If you eat the way he says, you're going to drink your broth first, and then you'll have all your noodles and chicken at the bottom. All right, here's my point for this. Let's all talk about sampling. The idea behind sampling is that we have a huge population, right? Big curve of all the people in the world, or all the instances of whatever it is that we're trying to observe. When we sample, it's like we're eating soup. Because a spoonful of soup is a sample. It's one spoonful of the soup. Just one. Does the first, if you eat soup correctly, does the first, let's call it scoop of soup. I've been waiting for that one. Does the first scoop of soup, should that taste any different than the last scoop of soup? Why? Not if you eat your food promptly. If you're one of my kids and you take an hour to eat, then yes, your soup's going to be cold. And no, I'm not going to heat it up again. But ideally, that first scoop should taste the same as the last scoop, right? Our food should not be a mystery of, I wonder what this bite will taste like. Like, that's not a fun game to play. That's like when you eat Jelly Bellies without looking at the color first. Like, you don't know if you're going to get a coconut or a popcorn, which is gross. It should all be thrown away. Okay? The idea behind soup is it's a bowl. It is the same flavor from first scoop of soup to last scoop of soup. Should be the same. Exactly. All right. Here's the other thing about sampling and why it works. So this is a corollary to how to eat soup. How many scoops of soup do you need to know whether or not you like it? It should just be one, right? One correct scoop of soup. Do you need to eat the whole batch? No. That's how a sample works, right? It's the idea that we have stirred the soup, we put it in a bowl, you stirred your bowl, you eat your soup, and then you can tell me whether or not you enjoy it or not, and whether or not you like my chicken noodle soup. You shouldn't have to go, I'll eat some more and find out. And the next thing you know, you eat the whole pot of soup, and you go, yeah, I didn't really like that much. Which is what my kids try to do to me all the time. They'll eat all their food and they say, I really want something else. I didn't like that. Dude, you ate a whole candy bar. You can't tell me you didn't like the candy bar. The candy bar tasted the same from the first bite to the 30th bite. You liked that candy bar. No, I didn't. I want something else. I want another one. Listen, kid. I'm not going to spank you because we don't do that in my house. All right. So this is sort of the logic behind sampling. To make a type 1 error says, we got a really strange scoop of soup. A really strange one. Like if you're Nike and you accidentally sample the shoe size of a basketball team. And you end up with Shaq's size 32 foot in your sample. Right? That's a strange scoop of soup right there. So there is an element of, and I like that the book uses this word, chance. There is a chance that we could get an odd scoop of the soup. It happens. But it should be chance. It should not be systematic. It should not be a systematic failure in how we collect our sample. I like it when kids try to help, but I really wish they wouldn't. Like, when you scoop soup out of a pot, do you know the correct type of spoon to use? A ladle. That's the correct spoon to use. What spoon does my 8-year-old daughter want to use? No, one with a bunch of holes in it. It's like, Abby, that's not going to work. What? It'll get it out. No, not really. A slotted spoon. So what's going to happen? Yeah, it's just going to fall through the slots. And all you're going to get is a bowl of chicken and noodles, which, again, is how I like my soup, but is not actually chicken noodle soup. And then somebody's going to complain because they didn't get any chicken noodles. His name is John, and he's going to pitch a fit. So no, Abby, you can't get the soup out of the pot because you suck at it. Because you don't know to use the right tools. It's bad enough we have chance. I swear, if these kids could count who gets how many noodles in each bowl, they would. Because dinner is never fair. Whether somebody got more milk than the other person, or somebody got more pieces of chicken, more noodles in their soup, dinner is never fair. But try explaining chance to a 4-year-old. I can walk him through, John, systematically. I have a pot of soup. I've stirred the soup. I have a ladle, not a slotted spoon. It's just chance, buddy. But I want that one. There you go. That's what you have to do. The only way to completely avoid a type 1 error is to never reject the null hypothesis, regardless of the evidence against it. This does not work for social science. It doesn't work, because then we could never say that anything is related to anything else. Ever. So we have to accept the possibility of type 1 error. We can reduce it. The main way in which we reduce it is by making sure that our errors truly are by chance and not because of something stupid that we've done, like pick the wrong spoon. That's why you guys should use surveys created by professionals and not just ask 30 of your friends. Because the professionals know what kind of spoon to use. They know how to stir a sample. They know what they're doing. Type 2 error is the one we're a little bit more willing to live with. In type 2 error, the null hypothesis is false, but we fail to reject it. And we conclude that no effect exists. With this situation, back to our taking a drug for a sickness thing, if we have a cure for your, or at least let's not say cure because that makes me sound really bad. If we have a treatment for your malady, but I tell you it doesn't work, what do? You don't take it, but what do? Yeah, at least you go off and find something else that we do believe works, right? So again, that's not as bad. There's no lost sort of opportunity cost there. Yeah, you didn't get the best treatment, but at least you're not getting a treatment that has no effect at all. Type 2 error is represented by a Greek capital B. That's a beta. Alpha, beta. But beta is a number that's hard to actually get to. Because if we knew what we were doing, we wouldn't have accidentally rejected a null hypothesis that we should have, or we wouldn't have accidentally not rejected a null hypothesis we should have. If we knew the true population values, we wouldn't be dealing with inferential statistics. We have sort of, again, using some logic here, working backwards, what we are interested in instead is what we call the power of a test. If a test has statistical power, power is then the ability to detect an effect when it does exist in the population. So we want our analysis to have statistical power. this for slide copiers. Why are we concerned about type 2 errors? Well, because it could result in non-communication of correct information. For us, practically, if we do a research design, we have a theory about how the world works. We collect data on that theory. We run the data. Turns out the data tells us that there's no relationship. Practically, what do we do with it? For the most part, in academics, we do nothing with it. So if I write a paper and I have a theory, let's say my theory is that, I don't know, good null finding. I should have thought about this before. Let's say my theory is that you are more likely to win an election when I don't know, something stupid, when you don't have a criminal conviction. So candidates who run for office that don't have criminal convictions make them more likely to win an election. Don't know where I got that from. Let's just say I do that study. And then I go out, I do the study, collect the data. I have no finding. That paper will never get published. Because you don't publish a paper that says there's no finding, that there's no result, that there's no there. And then, because I don't publish that paper, nobody knows whether or not being a convicted criminal makes you more or less likely to win an election. So there's a loss of information there. There's actually a journal. It was created years ago, and it was called the Journal of No Results. And the idea was that you would have these really beautiful papers that had great theories and concise literature reviews and collected data, and then you had no findings. And you would still publish it, so that way nobody else makes your same mistake. What we've done now is we've sort of moved to more of an open access version of academics, where you have your published work, then you also have a series of working papers that you started but haven't quite finished or haven't found an outlet for. And the idea is that you can at least claim, well, I did this work on this topic. And you can get your theory out there. Why does type 2 error take place? Well, again, chance. You could just have the wrong sample. The effects themselves could be small and are difficult to detect. So when we say that we can reject a null hypothesis because there is a statistically significant difference, that's true, but the actual size of the difference might be really small and hard to find. Or you could have just screwed up your research design. Maybe you used the wrong test. Maybe you forgot to do n-1 in a denominator somewhere. Maybe you should have done a pre-test, post-test design instead of just asking people whether or not they work out, because people are liars. Do you work out? Well, I wear workout clothes. Yes, I do. If everybody who wore workout clothes worked out, I think we'd be a lot healthier. It's like asking people, do you watch PBS? Yes, I do. Smart people do that. I'm smart. I do the thing that smart people do. No, you don't. You're a liar. So maybe you have a research design issue. Maybe you shouldn't have done a survey. Maybe you should have done a panel study instead. Okay. So the likelihood of these things happening. The likelihood of getting a correct decision is the probability of 1 minus alpha. The incorrect decision, that is alpha. So if this is 5%, this is 95%. We don't know what beta is. There are some tests out there to try to approximate beta based upon sample size and things like that. But a correct decision is the probability of 1 minus beta, if beta is our type 2 error. So again, it's the probability of not making a type 2 error. We call that statistical power. Controlling, we talked about that. So we kind of already talked about this. You can control type 1 error by making it more difficult to reject the null hypothesis. But the flip side of that is that if you decrease alpha, you're increasing beta. Practically, how can we help with type 2 error? Increasing the sample size, that usually is a good thing. The closer that we can get our sample to approximate a population, that's a better step. You could raise alpha, but this will increase your type 1 error. There are some people out there that do this, that they set alpha twice as big. Again, statisticians kind of cringe when we see that because we're like, no, because you don't realize what you're doing. You could use a directional alternative hypothesis. Again, this is accepted, but you really got to explain why you're doing it. Because what you're doing is you're shifting all of that area of rejection from 2 tails into 1 tail. It has to make sense theoretically. Increase between group variability. There's research designs out there that try to focus on extreme differences. So let's say if you're studying a bunch of countries, it might be best to study the outliers rather than all of the countries. It seems counterintuitive, but the idea here is that a lot of the sameness in your sample might be hiding or reducing the effect of the more extreme values. Bless you. Decrease with in-group variability. It's the opposite, the idea of looking at more of the same. These are really the two at this stage you guys should focus on. The idea of increasing your sample size, or I guess secondly, looking at directional alternative hypotheses. The sample size thing, I got an easy one. So this is something that is common in political science. If you're writing a research paper about a topic, the inclination is to always use the most current data available. So if I were going to do something on elections, I would look at the last few elections. When you do that, you could be throwing away decades worth of data. So back to our question, whether it's the abortion question or the spanking question. There are plenty of observations in the GSS from the last couple of iterations. So the 2016 GSS has 2,800 observations in it. That's a lot. That's enough to go from a t-score to a z-score, right? We are approximating infinity here with 2,800. That's a big number. So let's say you go ahead and you do your analysis and you find no results. There is no difference between men and women when it comes to abortion. Well, if you only look at the data from 2016, you're throwing out about 59,000 observations. And we do this in political science all the time. We want the most relevant, the most recent data. We've got a lot of data from the past. Include that as well. Go ahead and see. Maybe there's no gender difference today, but maybe there was a huge gender difference in the 1970s. Let's see if this difference changes over time. Another thing we tend to do is here, we tend to only look at the United States. There's data from people that live all over the world. In political science, we have something called the Afrobarometer, where we do these sorts of things in different countries in Africa. Australia, South America, Europe, they all have public opinion polling, but the social sciences in the United States, researchers like me, we just tend to look at data from the US. There is a lot more information out there than we think about. And we tend to not look at something, oh, well, that's old. That's old data. But what is it about your theory that says that it's only true today? Are you telling me that in the 1970s there was no such thing as gender differences? Or differences by political party? Or age? Or religion? Or any of that? So that's one way to increase your sample size is by by thinking about time. The other thing is that you can use a directional alternative hypothesis. It should be really clear the direction of the significance. Now, somebody here could probably make a valid argument for the directionality of opinion of differences between men and women. But there's a small problem with that. If I were to say that all women are more likely than men to support abortion rights, how could I be wrong? Because they may not be, because what are some alternative reasons for either support or non-support for abortion? Religion. Do women have religion? Really? Oh, well, it's good to know, being a man. I'd never considered that possibility. So you're saying that there might be some women out there who are less supportive of abortion rights than men? See, that's why I don't like directional hypotheses. Because you're making an assumption about your entire group if you're saying that they can only go in one direction. You might want to actually investigate that. You might want to take a look to see what is the distribution of women's views on abortion. I've got 5 minutes, don't I? Disagree with this. I don't like teaching people this one, but it is easy. No, I'm not going to do it. Yeah, this will just confuse you too. All right. Here's what we're going to do next week. We're going to look at different groups. So all the examples we've done so far have been that 2 by 2 kind of example. Like, what if you have a variable that's not 2 groups? What if you have a variable that's multiple groups, like, religion, where there's more than 2 religions? What are we going to do then? It's called the chi-square. We'll do that next week.